Hello, in this lecture I will explain what is mathematical induction. Mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. A natural number is a positive integer like 1, 2, 3, 4, 5, 6, 7, etc. And actually we have two stages in mathematical induction. In the first stage we will verify that the statement is true for n that equals to 1, or we will check whether the statement is true or not for n that equals to 1. And only after we passed the test, that is to say only after we found out that the statement is indeed true for n that equals to 1, then we will proceed to the second stage. And in the second stage we will assume that the statement is true for n, and then when we rely on this assumption, we will prove that the statement is also true for n plus 1. So actually in the second stage we will create two equations. The first equation will be the expression of the statement for n, and actually it will be the induction's hypothesis or induction's assumption. And actually we assume that the expression of the statements for n is true, and when we rely on this assumption, we will prove that the expression for the statement for n plus 1 is also true. Okay, so we rely on our assumption that the statement is true for n, and by that, when we rely on that assumption, we will prove that the statement is also true for n plus 1. Okay, so the second expression will be the expression of the statement for n plus 1, and that equation we have to prove that it is true. And I will repeat again, we will rely on the assumption that the first equation is true, that is the induction's hypothesis is true. And when we rely on this assumption, we will prove that the second expression for the statement, the expression of the statement for n plus 1 is also true. Okay, so now I will explain the logic behind the proof by mathematical induction. Actually, you should remember that in the first stage we verified that the statement is true for n that equals to 1. Okay, so we know for sure that the statement is true for n that equals to 1. And in the second stage, we proved that if the statement is true for n, then it also must be true for n plus 1. So actually we know that the statement is true for n plus 1, and we can deduce from our general proof that if it is true for n, it also must be true for n plus 1, that it also must be true for 1 plus 1. Now n equals to 1, and it also must be true for 1 plus 1, that is 2. And it must be true according to our general proof that if it is true for n, it also must be true for n plus 1. Okay, so in this way we actually proved that it is also true for n that equals to 2. And again we will repeat on the same process in order to prove that the statement is true also for 3, for n that equals to 3. We will say that now we know that the statement is true for n that equals to 2, and according to our general proof that if it is true for n, it also must be true for n plus 1, we can say that because of the fact that we know that it is true for n that equals to 2, it also must be true for 2 plus 1. Okay? For 2 plus 1, that is 3. And then we also continue in the same way. We will say that we know now that the statement is true for n that equals to 3, and according to our general proof that if it is true for n, it also must be true for n plus 1, so we can deduce from that general proof that because of the fact that the statement is true for n that equals to 3, it also must be true for 3 plus 1. That is 4, and so on and so on. We will continue in this way to prove that is also true for n that equals to 5, 6, 7, etc. So actually we can say that by the first stage, by doing the first stage, that is to say to verify that the statement is true for n that equals to 1, and then by proving in the second stage that if the statement is true for n, it also must be true for n plus 1, we actually proved that the statement is true for all the natural numbers, and I actually explained to you why it is true for all the natural numbers, because we will start to prove step by step that it is true for 1, and then for 2, and for 3, for 4, 5, 6, 7, according to what I have already explained to you. So in this way we actually proved that the statement is true for all the natural numbers. Okay, so that is the logic behind mathematical induction's proof. Okay, so now in order to clarify the topic, I will give you two examples. Okay, so we'll start. We will start from the first example. The example is 1 plus 2 plus 3 plus n equals to n times n plus 1, all divided by 2. So we have to prove that 1 plus 2 plus 3 plus 4 plus n equals to n times n plus 1 divided by 2, and we actually have to prove that this statement is true for all the natural numbers. Okay, so we will start with the first stage. That is to say, we will verify that this statement is true for n that equals to 1. Okay, so in this side of the equation we will have only 1 because n equals to 1, and 1 equals on the other side of the equation we have n times n plus 1 divided by 2, and n equals to 1, so it will be 1 times 1 plus 1 divided by 2, and this is actually equals to 1 times 1 plus 1 is 2 divided by 2, so it is 1 times 2 is 2 divided by 2, 2 divided by 2 is 1. So we have here identity, 1 equals to 1, so we actually passed the first test. I will repeat again here. In this side of the equation we have only 1 because n equals to 1. In the other side of the equation is n times n plus 1 divided by 2, and n equals to 1, so it is 1 times 1 plus 1 divided by 2, and 1 plus 1 is 2, 1 times 2 divided by 2, and 1 times 2 is 2 divided by 2, 2 divided by 2 is 1, so 1 equals to 1. So we can say that this statement is true for n that equals to 1, and after we verified it we can proceed to the second stage, and in the second stage we actually assume that this statement is true for n, and as when we rely on this assumption, we will prove that the statement is true for n plus 1. So we have to create two equations. The first equation will be the actually inductions hypothesis, or inductions assumption. Inductions assumption that the original statement is true for n. So we will create the statement of the expression of the statement for n. It is actually exactly the same expression of the original expression itself. So we'll copy the statement as it is. It is 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So the first equation is the inductions hypothesis or inductions assumption. We assume that this equation is true, and when we rely on this assumption, we will prove that the original statement is true for n plus 1. So now we will create the expression of the original statement of this statement for n plus 1. And then we will prove that this statement for n plus 1 is true, as we rely on our assumption that the statement for n is true. Okay, so the expression for n plus 1 will be 1 plus 2 plus 3 plus n plus n plus 1. Yes, we will have also to add also n plus 1, because this expression is for n plus 1. Okay, so in this side of the equation we will have to add numbers until n plus 1, that includes also n plus 1, because this expression is for n plus 1. And in the other side of the equation, the expression for n is n times n plus 1 divided by 2. But we need the expression for n plus 1. So wherever it is written n, we will substitute it by n plus 1. So the expression for n plus 1 will be, as I already said, in the original expression it is n times n plus 1, so it will be n plus 1 times n plus 1 plus 1. Because in the original expression we have n times n plus 1, so it will be n plus 1. We open the brackets, and in the brackets, instead of n, we will write n plus 1, and then we will have to add 1, so it will be n plus 1 plus 1, and we divide all by 2. So actually the second equation is the expression of the statement for n plus 1, and we have to prove that this second expression is true. Okay, so it is 1 plus 2 plus 3 plus n plus 1 equals to n plus 1 times n plus 1 divided by 2. As I already said, we substituted n by n plus 1. Wherever it is, it was written n in the original statement, we wrote n plus 1 because this expression is for n plus 1. And we have to prove that this expression for n plus 1 is true. So in order to prove that this equation is true, first of all, we know that n plus 1 equals to n plus 2, so we will write it down. So instead of n plus 1 we will write n plus 2 all divided by 2. So the only change that I did from this line to this line is I changed n plus 1 to n plus 2, and all the other things are the same. I copied it from here to here. Okay? So now we have to prove that this statement for n plus 1, this equation for n plus 1 is true. Okay, and we will rely on our induction assumption that the statement for n is true, that equation 1 is true. Okay, so if we look on this expression, 1 plus 2 plus 3 plus n, we can see immediately that this expression is exactly the same as this expression. So they are exactly the same. But as we see here, this expression equals to n times n plus 1 divided by 2. So we can say that this expression that equals to this expression also equals to this expression. Okay, so we can substitute this expression by n times n plus 1 divided by 2. Okay, so we will do it now. So instead of 1 plus 2 plus 3 plus n, we will write n times n plus 1 . n times n plus 1 divided by 2, and the other parts of the second equation of this second equation, we will copy it as it is. The only change that I did is substituted this expression by n times n plus 1 divided by 2. As I already told, they are equal to each other, so we can substitute one by other one. So this is the only change, and the other parts of the equation will be the same. So I will copy the other parts as it is, so it will be plus n plus 1 equals to n plus 1 times n plus 2 divided by 2. Okay, so I substituted this expression by n times n plus 1 divided by 2 because they equal to each other, and n plus 1 I copied it here equals to n plus 1 times n plus 2 divided by 2. So I copied it to this equation. So we will have to prove that this statement is true. Okay, so in order to prove that this statement is true, the statement for n plus 1, we will divide both sides of the equation by n plus 1, because we have on both sides the expression n plus 1, so we will divide both sides of the equation by n plus 1. And then we will get that n times n plus 1 divided by n plus 1 is n. We divide it by 2 plus n plus 1 divided by n plus 1 is 1 equals to n plus 1 times n plus 2 divided by n plus 1 is n plus 2. So I will repeat again, n times n plus 1 divided by n plus 1 is n, we divide it by 2, n plus 1 divided by n plus 1 is 1, and n plus 1 times n plus 2 divided by n plus 1 is n plus 2, we divide it by 2. So here actually we can separate this expression to two parts. It will be here n divided by 2 plus 2 divided by 2. Okay, so we will write it down. So after we divide this expression to 2, we get that it is actually n plus 2 divided by 2 is n divided by 2 plus 2 divided by 2, and 2 divided by 2 is 1, so we will write it down. So it is n divided by 2 plus 1 equals to n divided by 2 plus 1. So actually we got an identity that says n divided by 2 plus 1 equals to n divided by 2 plus 1. So we actually proved that the second expression for n plus 1 is true, and we proved that if the statement for n if the expression for n for this statement is true, the expression for n plus 1 must be also true. So we actually, by completing the two stages of the proof, we actually proved that this statement is true for all the natural numbers. Why? Because I have already explained to you why, by doing the two stages of the proof, we actually proved the statement for all the natural numbers, and I will not repeat on the explanation, but we will move to the second example. So the second example will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared, all divided by 4. So actually we have to prove that 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared divided by 4. And we actually must to prove that this statement is true for all natural numbers. So, in order to prove that this statement is true for all the natural numbers, we'll start with the first stage. That is to say, we will verify that this statement is true for n that equals to 1. Okay, so if n equals to 1, we have in this side of the equation 1 to the power of 3 equals to n squared times n plus 1 squared divided by 4, but n equals to 1, so it will be 1 squared times 1 plus 1 squared divided by 4 equals to 1 squared is 1, 1 plus 1 is 2, so it is 2 squared divided by 4 equals to 1 times 2 squared is 4 divided by 4 equals to 4 divided by 4 is 1, and 1 to the power of 3 is 1 equals to 1. Okay, so we have here an identity, 1 equals to 1, so we actually verified that this statement is true for n that equals to 1. So we passed the first stage, and we can move to the second, we can proceed to the second stage. That is to say, we will assume that this statement, the original statement, is true for n, and when we rely on this assumption, we will prove it for n plus 1, or we will prove that this statement is also true for n plus 1. So we have to create actually two equations. The first equation will be the induction hypothesis, so the induction hypothesis will be that the expression for n is true. Okay, so the expression for n is actually exactly the same as the original statement itself. So we will copy it. The expression for n is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared divided by 4. Okay, so this is the expression for n, and actually this is the induction hypothesis, that the expression for n is true, that equation 1 is true. It is exactly the same as the original statement. Now, when we rely on this assumption, we will prove that the expression for n plus 1 is also true, or the expression of the statement for n plus 1 is also true. So we will write down the expression for n plus 1 of the statement, and then we will prove it that it is true as we rely on our assumption that equation 1 is true, that the induction hypothesis is true. Okay, so the second expression for n plus 1 of the statement will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3, because we now create the expression for n plus 1, so we will add numbers until we get to n plus 1, and it also includes n plus 1. Okay, so in this side of the expression, it is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3, and all equals. So remember that it is expression for n plus 1 of the statement. So wherever it is written in the original statement n, we will substitute it by n plus 1 because this is the expression for n plus 1. So in the original statement we have n plus 1, we have n squared, so we'll substitute it by n plus 1 squared. And in the brackets we have n plus 1 squared. So instead of n, we will write n plus 1. We have also plus 1, so we will add 1. And all squared divided by 4. So instead of n, we wrote n plus 1 for the expression for of the statement for n plus 1. So we actually got that 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3 equals to n plus 1 squared, because we substituted n by n plus 1. And again we substituted n by n plus 1, so it will be, instead of n plus 1 square, it will be n plus 1 plus 1 square. Okay? So we know that n plus 1 is n plus 2, so we will write it down. One to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3 equals to n plus 1 square times n plus 2 square, because n plus 1 plus 1 is n plus 2, all divided by 4. Okay, so here the only change that we did, if we compare it to this line, we wrote instead of n plus 1 plus 1, n plus 2, or n plus 1 plus 1 square, n plus 2 square. All the other things is exactly the same. We copied it here. So this is the expression of the statement for n plus 1 that we have to prove that it is also true. When we rely on the assumption that the expression for n is true, that is the induction hypothesis. So if we look, in order to prove it, to prove that the second expression for n plus 1 of the statement is true, we should look on this expression 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 is exactly identical to this, and this expression equals to n squared times n plus 1 squared divided by 4. So because of the fact that this expression is identical to this expression and this expression equals to this expression, we can say that this expression is equals to n squared times n plus 1 squared divided by 4. So we can substitute this expression by this expression, that is n squared times n plus 1 squared divided by 4. Okay, so we'll do it now. So it will be, instead of this expression, we will write this expression, because they are identical, they are equal to each other. So we will write n squared times n plus 1 squared divided by 4. And the rest part of the equation that we have to prove, we will copy it as it is. So it will be plus n plus 1 to the power of 3 equals to n plus 1 square times n plus 2 square, all divided by 4. Okay, so I will repeat again. We substituted this expression by n squared times n plus 1 squared divided by 4 because they are equal to each other, so we can substitute one by the other. And the last part of the equation is exactly the same as this part. We actually copied it to here. So this expression for n plus 1 of the statement, that equation, we have to prove that it is true. So in order to prove that this expression is true, we will divide both sides of the equation by n plus 1 square, because we have n plus 1 square in both sides of the equation. Okay, so we'll divide it by n plus 1 square, and here we'll get that n square times n plus 1 square divided by n plus 1 square will be n square. So it is n squared divided by 4 plus here n plus 1 to the power of 3 divided by n plus 1 square will be n plus 1. All equals n plus 1 square times n plus 2 square divided by n plus 1 square will give us n plus 2 square. Okay, and we divide it by 4, of course. Okay, so this is the outcome after we divide this equation by n plus 1 square. Here we can multiply both sides of the equation by 4. Okay, so n squared divided by 4 times 4 is n squared, and n plus 1 multiplied by 4 is 4 n plus 1 equals to n plus 2 squared divided by 4 times 4 is n plus 2 square. Okay, so this is the equation after we multiplied both sides of the equation by 4. N squared divided by 4 times 4 is n squared. N plus 1 times 4 is 4n plus 1, and n plus 2 squared divided by 4 times 4 is n plus 2 squared. So here we will open the brackets in both sides of the equation. So we got in the identity. I'll explain what I did. Here it is n squared, so we go with n squared to here, and 4 times n is 4n, 4 times 1 is 4, and n plus 2 squared equals to n squared plus 4n plus 4 according to the formula that a plus b squared equals to a squared plus 2ab plus b squared. Okay? So actually we proved that the statement for n plus 1 of the original statement of this statement is true, or we can say that we proved that if the statement for n is true for this, we proved actually that if the expression for n is true for this statement, the expression for n plus 1 must be also true. Okay, so if we combine both sides of the stages, in the first stage we proved that this statement is true for n that equals to 1, and in the second stage we proved that if this statement is true for n, it must be also true for n plus 1. And we can say that we proved actually that this statement is true for all the natural numbers, and this is exactly what we wanted to prove, that this statement is true for all the natural numbers. Okay, and I have already explained to you why we can deduce from the two stages of the proof that this statement is true for all the natural numbers, so I will not repeat on the explanation, but we will summarize the lecture about the mathematical induction, and we can say that mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. A natural number is a positive integer like 1, 2, 3, 4, 5, 6, 7, etc. And we actually do two stages in mathematical inductions proof. In the first stage, we will check that the statement is true for all the natural numbers, and only after we verified that the statement is true for all the natural n, in the first stage we have to prove, in the first stage we will prove that the statement is true for n that equals to 1, and only after we verified that the statement is true for n that equals to 1, we will proceed to the second stage, and in the second stage we will prove that if the statement is true for n, then it must be also true for n plus 1. And in this way we actually proved that the statement is true for all the natural numbers, and I will explain briefly why. Because in the first stage we proved that the statement is true for n that equals to 1, And in the second stage, we prove that if the statement is true for n, it also must be true for n plus 1. So we can say that now that we know that the statement is true for n that equals to 1, and we proved already that if it is true for n, it's also true for n plus 1. So because of the fact that it is true for n that equals to 1, it also must be true for 1 plus 1, that is 2. According to our general proof, that if it is true for n, it also must be true for n plus 1. Okay, so in this way we proved actually that the statement is also true for n that equals to 2. And after we know that the statement is true for n that equals to 2, we can repeat on the same process in order to prove that the statement is true for n that equals to 3. Because we can say that now we know that the statement is true for n that equals to 2, and we have already proved that if it is true for n, it also must be true for n plus 1. So now that we know that it is true for n that equals to 2, it also must be true for 2 plus 1, that is 3. Okay, according to our general proof, that if it is true for n, it also must be true for n plus 1. Okay, so in this way we proved that the statement is true for n that equals to 3. And after we know that the statement is true for n that equals to 3, we again can say that we can rely on our general proof that if it is true for n, it also must be true for n plus 1, that the statement is true also for 3 plus 1, that is 4. Okay, so in this way we will prove that the statement is true for all the natural numbers. Okay, thank you very much.